Hello, Professor Borrelli. My name is Zheng.
My name is Mingguang Zhou.
My name is Bowen Wang.
My name is Zack.
My name is Guanqun Huang.
My name is Yuchen Zheng.
Our project topic is MPC controller design and implementation for optimal trajectory with lowest time consuming based on Turtlebot. The challenge of this project is that it's hard to control the Turtlebot to check the trajectory and avoid hitting the obstacles in high accuracy. Our design aims to provide better tracking accuracy and obstacle avoidance for Turtlebot. In software part, we use A-star search to plan global paths, use MATLAB MPC to check local trajectory, and use Simulink to visualize the model. Our team also did some measurement to figure out the error.
Our dynamic system in Figure 1 is based on the general dynamic module of the wheel robotics. We set up an experiment to measure the physical properties like the mass, the moment of inertia, the maximum acceleration limitation. So, based on the dynamic module of the TWIP, we can get the equation of motion from the time k to time k plus 1, where the state vector x, v, is the linear velocity of the turtlebots. X and y are the position of the center of mass. Theta is the angle. And the input vector TL, TR represent the torque of the left and right wheel roll motors. TS is the interval times which we set up 0.1 here. The definition of other parameters can be found in the appendix. Since the RS system of the turbobots can support linear and angular velocity input, we actually use the TL and TR only in the MPC computation and deliver the optimal velocities to the turbobots after open loops prediction.
This is the team's very first time to interact with Turtlebot, so we would like to know more about the dynamic behavior, especially in errors. Therefore, a number of experiments and analyses were performed on the Turtlebot. There are two major goals. First of all, to find the proper linear speed and angular speed. Secondly, help the team figure out what are the main error contributors. In the linear experiments, we tried different speed values and recorded errors in each scenario. In the end, we chose to use linear speed 0.1 meters per second because the errors are more reasonable and controllable compared to other speeds. Also, we found that in the linear movement, there is almost no left or right deviation. In the angular experiments, based on the planned path results, it requires a sharp turning, so we did the test against 30 degrees per second and 90 degrees per second to check feasibility under each angular speed. Results turned out well. There's also no obvious left or right deviation. According to all test results, we concluded that in short distance, the major error contributors are acceleration and deceleration, but in long and continuous running, the friction plays a bigger role.
Why we need to use A-star algorithm? If we use MPC from start point to the end point all the way around, it will cost months of computation time and increase the uncertainty of the optimal solver. Therefore, in this project, we use an improved version of A-star algorithm. Firstly, we partition the environment into 1000 times 1000 grid map and add the obstacle into the map. Then we dilate the obstacle by size of the turtlebot and random noise. As to the algorithm's improvement, we change the loss evaluation mode and improve the point selection mechanisms by modifying the data type and heap structure. As the result shows, under the same experimental condition, the outcome path is the same, but the speed of the computation is 20 times faster than the general A-star.
Use model predictive control for local trajectory tracking. This picture shows the open loop prediction and closed loop simulation at time step k and s. These black points are the plan paths from a A-star algorithm. In the open loop prediction, we have initial state xk. Then the controller will find some reference points from the planned path to build the cost function for optimal control problem. As shown in picture, we use binary search to find the closest point to the current point xk. Then pick the reference point every several points. The reason why we use reference points and select in a relatively large scale is that we need to keep the real trajectory closer to the planned path and detect the turning point early to avoid sharp turning. You can see that there is an obvious turning motion at time step S. And these are the parameters of our optimal problem. Our Q value is larger than P value because we need the real trajectory keep close to the planned path. And we also add the input rate in the cost function to avoid sharp turtle changing. Since we pick the reference points in a large scale, we can detect the endpoint early and enter a deceleration MPC process. In this problem, we only use the endpoint as reference point, but we need to change the p-value and q-value to make sure the Turtlebot decelerates to 0 at the end of the trajectory. But we didn't add the terminal constraint to the problem because our prediction period n is relatively smaller than the whole scale. So Turtlebot can't reach the endpoint at n step. So we just add the endpoint to the cost function.
Here is a chart of comparison between the MATLAB simulation and the actual Turtlebot trajectory. The red squares here represent the obstacles, the red dot lines represent the MATLAB simulation path, and the blue dot line refers to the actual path of the Turtlebots. Here you can see the general trends that the actual Turtlebot trajectory follows pretty well with the MATLAB simulation. This is another chart to compare the input of the left wheel torques and right wheel torques. The general trend here is similar, but we can tell the difference that when the simulation torques are 0, the actual input torques are with some constant values. This is because in the actual situation, there are some torques to accelerate to try to overcome the speed and angle errors of the Turtlebot. Besides that, the actual torques generally follow the trend of turning as the simulation. Thus, it proves again the actual trajectory follows well with the simulation.
There is a demo about the real-time Turtlebot running. As we can see, it follows the tracking trajectory and avoids to hit obstacles. This result proves that the real Turtlebot trajectory and the MATLAB simulation both have a good accuracy. If possible, our team could improve robust of system to different scenarios. What's more, we can add a perception stack using LiDAR to build real-time obstacle avoiding control system. This project could apply to the autonomous driving in the future. That's all about our presentation. Thank you for watching and hope you can enjoy it.